All right. So what we're going to go over today, guys, hopefully will be review for you, okay? And you'll find that whenever we have a lesson where I'm kind of lecturing for a bit, okay, it's going to start out with key points, okay, which is kind of telling you here's the really important things that are probably going to show up as either, you know, a written response item or there'll be a lot of marks on an exam kind of thing on those, all right? Those would also be things that would probably show up on a quiz, okay, like on Thursday, okay? All right, so we want to understand how the theories of the structure of the atom were developed, because there were many, okay? As obviously we get more knowledge and equipment gets better and we discover new things, okay, our ideas have to change, okay? That's how science works, and that's probably the most important thing you can get out of today is that science works like this. We keep a model until something comes along that says it doesn't work anymore, okay? Then we have to make up a new model. All right, nothing's ever written in stone, all right? I mean, we say, you know, there's this law and there's that law. Well, yeah, they're laws because we haven't found anything that says they're not true. Okay, so we keep them around. Okay, theories are similar. Okay, theories are things that have been proven over and over again. Okay, and they're a model that fits something. Okay, they'll stay around until we find something that disproves them. Okay, then we have to come up with something else. And we'll go over the parts of the atom and their characteristics. Okay. All right, so we're going to start out here first with kind of the early beginnings of chemistry, okay? The first kind of chemistry, it wasn't real chemistry, okay? The first work on chemistry, anyway, that came along would have really been done by, okay, primitive peoples, okay? People used chemical reactions to do things, okay? They didn't know that's what they were doing, but that's what they used, okay? Things to, you know, dye cloth, tanning leather, preparing food, okay? For a long time, okay, people used cured salts, like curing salts and stuff on meat to keep them from spoiling. All right, you guys know what I mean? Like making jerky. Okay, it's like curing meat. Okay, smoking something. Okay, is the same. That's kind of cures it, and it keeps mold and bacteria and stuff from growing on the meat and spoiling it for a longer period than just leaving the meat out. All right, people knew for a long time that there was something in there that kept the meat good for longer. Okay, so they did. They didn't realize that it was, you know, salts and things like that that kept bacteria from growing. Okay, it just worked, but it's chemistry. Okay, all right. Eventually, when people were not just living day to day and, you know, trying to find enough food to eat to survive, okay, and they had a little more time on their hands, they began to search for explanations to why these things worked. Okay. All right. The first idea of the atom. Okay, first idea of the atom, no surprise, was developed by a Greek person. Okay, the Greeks were the first kind of real thinkers. In fact, this was the job of a lot of people. Aristotle, okay, he was a thinker. Plato was a thinker. Okay, and this guy, Democritus, was a thinker. Being a thinker in ancient Greece was like the best job you could have, okay? Because you were widely respected by everyone. You sat around in the Acropolis and people fanned you with palm fronds and fed you grapes all day, okay? So it was a pretty sweet gig, and you just had to come up with ideas, all right? Democritus came up with this idea that matter wasn't made of the four elements that everyone thought it was made out of, okay? Everyone thought that everything was made out of earth, air, fire, and water, okay? They had kind of a rudimentary periodic table, okay, that worked for everything, all right? Lava, for example, okay, was some parts fire, some parts earth, and some parts water, okay? Now, that's actually not all that far off, okay? Granted, fire's not an element, but it was really hot, okay? And it was made up of rock, and there's lots of steam and stuff like that that comes out of lava. That really, I mean, it made sense. Their idea of these four elements was logical. Okay, if they were, let's say, working with, let's say, meat. Let's say they had caught a fish. Well, fish were some parts earth because they had solid parts, okay, and they were some parts water, okay. So, you know, they kind of had this mixture. Everything was made up of these percentages and things like that. Steam was some parts water and some parts air. Made sense. You could only get steam by heating up water, and then it turned into this airy stuff. Well, some parts water, some parts air. Okay, so they had this idea. Democritus said it can't be that simple. He thought that everything had to be made up of these tiny, indivisible particles that were so small we couldn't see them. Okay, now, problem is, when you come up with an idea that goes against a widely accepted idea, people aren't all that willing to go for it. Okay? They're like, Democritus, that's a dumb idea. You're a thinker, but that's a dumb idea. We already got the 4 elements over here. Okay, Aristotle says this is what everything's made of, and he's smarter than you. Okay, and it makes sense. So, yeah, take your atom idea and shove off. All right. Well, it wasn't all bad for Democritus. He did come up with something good. Anyone know what it was? What's his name sound like? Democracy. Okay, so it wasn't all bad for Democritus. He just stopped thinking about science and started thinking about other things. Okay, all right. As a result, though, because his idea wasn't widely accepted, it just was forgotten. Okay, and 2,000 years later, okay, it came kind of back to light. Okay, during the Middle Ages, so again, still before chemistry is really a science, okay, there was a group of people who were playing around with chemicals. And I say playing around with chemicals, I'm not being facetious. That's really what they were doing. Okay? They were just mixing stuff together, trying to make a couple of things. The elixir of life, okay? They were trying to turn cheap materials into gold and silver and things like that. Okay? They were trying to like transmute lead and things like that into valuable stuff, right? They were the alchemists. Now, the problem is all the stuff they were trying to do is impossible. But in the process of trying to do it, they discovered a lot of things. Okay? Unfortunately, because they were in kind of rabid competition with each other, they didn't get a lot of communicating done. Okay? And so unfortunately, a lot of those discoveries were kind of lost and then rediscovered later. Okay? I'm sure that some of these guys discovered gunpowder several times. Okay? Gunpowder is just one of those discoveries that, you know, you have to make once or twice, maybe 3 or 4 times before someone finally lives long enough after the discovery to tell people about it. Okay? But they essentially were trying to do something that's impossible, but at the same time, they were messing around with chemistry. Okay? They were mixing things together, finding out that certain things had certain properties or acted in certain ways in certain situations. Okay? And that sort of led to the development of the science of chemistry. Okay? So these two guys, okay, Antoine Lavoisier and Roger Bacon, okay, took a lot of that material and turned chemistry into a legitimate science. Okay? Rather than a trial and error, mix this with that, they brought in the scientific method. Okay? Let's investigate this problem. Let's come up with a hypothesis. Let's test it. Okay? Let's analyze our results and move on from there. Okay? They were kind of the guys who came up with the scientific method and turned alchemy into chemistry. All right. So, the idea of the atom. Okay? The idea of the atom is this. Just like Democritus said, everything is made up of tiny, indivisible particles. Okay? Not invisible, indivisible. All right? That means that you can't cut them. All right? Now, can you split an atom? Some atoms. Okay? You can't split a hydrogen atom. It's too small. Okay? But yes, bigger atoms you can. You can, with nuclear fission, you can split them. But you can't take a knife and cut them. All right? In that way, they are indivisible by sort of any natural means. All right, everyone follow me there? Okay? Thankfully, that's true, right? Otherwise, if you were cutting a carrot at home, you could split the atom on the cutting board. Right? That would kind of be bad. All right? So, no, that's not possible. Mostly because your knife is millions of atoms across. Okay? Even though it's really sharp and looks really thin when you look at it edge on, okay, it's still thick from an atomic level. Okay, if you've ever seen like an electron microscope picture of the sharp end of a pin, it actually looks blunt. Okay, to us, to our eye, it looks very sharp, and it is quite sharp. Okay, but okay, at a microscopic level, it's quite blunt. Okay, so we take this small cube of an element. Let's say we take like a cube of iron. Okay, so we just got a little cube of iron, and we got this magical knife or laser that can cut it. Okay, and we keep cutting it into smaller and smaller pieces. Eventually, the pieces would get so small we wouldn't be able to see them anymore. Okay, that would be getting somewhere near, okay, let's say atomic level. Now here's the thing about every atom of that block of iron. They're identical. Why do they all have to be identical? Because iron's an element. Okay? It's not a compound. It's not made up of other things. Okay? It's a pure substance. It's an element. Okay? It cannot, when I get down to the element level, okay, to the atom level, every single atom looks the same. They have to be, or they won't be iron. Okay? So if we're looking at iron, okay, every one of those atoms, okay, would have 26 protons, okay, and they'd have 29 neutrons, okay, something like that. Okay, but they would all be exactly the same. All right. So eventually, like we said, we reached the point where the particle of lead could no longer be divided, okay, and still retain its properties. When you split an atom of, let's say, uranium, okay, in a nuclear reaction, do you still have uranium after? No, you don't. Okay. When you break it, okay, now you have smaller chunks. Those are smaller atoms of other things. In fact, it usually breaks down into forms of lead afterwards. Okay. So you have this radioactive lead material, okay, after a nuclear fission reaction. You don't have uranium anymore. All right. Okay, so the atom is the smallest particle of an element, okay, that still retains the properties of that element. So it still has the same melting point, boiling point, density, okay, all of that kind of stuff. Okay, questions on that so far, guys? Okay, if you ever got a question, don't be afraid to ask. Okay, just put your hand up and let me know. All right, late 1700s. So, you know, around 300 or 400 years ago, chemists started noticing a few things. Okay, they started noticing that when chemical reactions happened, they always seemed to get certain ratios of the products. Okay, so they'd start out with, let's say, twice as much of one thing as they had of the other, and when they got the reaction going, they got a similar ratio on the other side. Okay, and that led to this idea that there must be small parts that are doing some sort of dance or switching or doing something during this chemical reaction, because they always noticed they noticed obviously these ratios, but they also noticed that whatever the mass of what they started with was, that's the mass of what they got at the end. Okay, you guys have heard of the law of conservation of matter before, right? Okay, that was kind of an important discovery. Okay, that led to this idea that matter must be made of smaller pieces. These smaller pieces are always conserved. They don't get destroyed. Okay, they have to end up going other places because they knew, you know, the properties of what they started with were different than the properties of the stuff they ended with. So John Dalton kind of was the first person to put this down on paper. That's how science works. If you're the first person to put it on paper, it's your law or your discovery or whatever. Okay? So Dalton's atomic theory, because he's the first one to put it on paper, goes something like this. Okay? Would these 4 points be a good quiz item? Probably. Okay? They're also a great multiple choice question on a unit exam. Which of the following is not part of Dalton's atomic theory, right? It's pretty easy to make one up for that. All right, first point. All elements are composed of tiny indivisible particles called atoms. Okay. The other points are essentially the proof. Okay. Second point, atoms of the same element are identical. Okay. Why they have this atoms of any element are different from those of the others, that seems redundant to me. Okay. Obviously, carbon atoms are different than oxygen atoms, but all oxygen atoms are identical. All carbon atoms are identical. Okay. That's the only way that they can have the same physical properties, is if they have the same number of protons, same number of neutrons, same number of electrons. Okay. All right, 3 and 4, okay, are the ones that talk about sort of the proof of this in chemical reactions. Okay. Atoms of different elements can combine with one another in simple whole number ratios to form compounds. Okay, this is something that people noticed when they started mixing two things together and only got one material at the end. Okay, same mass on both sides. Well, those two materials somehow joined together chemically. Okay, for example, if we took, let's say this. Okay, hydrogen and oxygen, okay, go together to make water. Agreed? I got to put a 2 over here though. Okay? Now, what do you notice? Everything is a whole number, right? I never have half of an atom in a compound, right? Okay? That's what they mean by simple whole number ratios. You can't have this, HO 1/2. All right? I can't have half an oxygen atom. If I have half an oxygen atom, I have beryllium, I guess. Okay? That's not right. Okay, I can't have half of an atom. An atom is the smallest particle of a substance, okay, that can exist. Everybody with me there? So that's what they mean by this simple whole number ratio part. This It doesn't happen. If it does, you split the atom somehow, and that's no longer that reaction. It's kaboom. Okay? All right, and fourthly, chemical reactions occur when atoms are separated, joined, or rearranged. Okay? I don't change the atoms. I just change who they're with. But the atoms themselves stay the same. Okay? That was the thing the alchemists didn't get. Okay? The alchemists thought, well, if I do some sort of weird chemical thing, I can do this, and I can turn lead into this. No, you can't. Those are two completely different things. Okay? Here's the problem. They thought they saw themselves do that in other kinds of chemical reactions. For example, maybe they had, I don't know, something like this. Okay, so what I'm showing you here is a chemical reaction between copper and silver chloride. Okay, if I put these two things together, okay, over the course of a few hours, okay, the copper will start to turn silver because of the chemical reaction that's going on. Okay, the silver and the copper are switching places. Everybody follow me there? Okay, and so what you'll end up getting is if you had like a penny in there, okay, the penny will get plated with silver. It'll look silver when you're done because it'll be covered with silver. You're not going to get rich on this reaction because silver chloride's expensive. Okay, people thought of that. All right, but alchemists would have seen this as saying, look, I turned this into silver. I'm amazing. Okay, but they didn't really turn it into silver. They started out, they had silver there to begin with. Okay, have they changed anything? Have they changed any of the elements in this reaction? They've changed the compounds. They've separated things. They've rearranged things. They've joined things. But they haven't changed anything. They started out with copper, silver, and chlorine, and they ended with silver, copper, and chlorine. Okay? They didn't change any of the elements. They just changed where they were. All right? That's what they're saying in statement number 4. Okay? All right. All right, so generally this theory has been accepted over the years because there's nothing come along to say it's wrong, other than that whole they're completely indivisible part. Some atoms, yes, are dividable. Okay, in a nuclear reactor or in a nuclear bomb, yes, certain atoms can be split. Okay, anyone know how they do that? Right, they shoot neutrons at them. Okay, in a nuclear reactor. It's obviously a lot more controlled and refined. Okay? In a nuclear reactor, there are fuel rods. They're exactly like they sound. They're a big metal rod. Okay? And on these rods are little pellets of enriched uranium. Okay? They move that rod into the path of a bunch of neutrons that essentially get shot at it. Okay? When those neutrons hit the uranium splits. Okay? And large amounts of heat are released. Okay, this all, of course, has to be done underwater. Okay, because the water heats up, turns into steam. The steam turns a turbine, and that's how you generate electricity with nuclear power. Okay, if you want to generate more electricity, you drop more of the rod into the path of the neutrons. If you want to generate less electricity or it's starting to overheat, you pull the rod out. Okay, so that's how a nuclear power plant works. Okay, in a nuclear bomb, obviously, you don't want the process to be very controlled. You want it to happen fast. Okay. So they take a big chunk of the fissile material, uranium, plutonium, whatever it's going to be, and they surround it in a container of high explosive. Okay? Plastic explosive, C4, okay? Sometimes it's even just TNT, okay? Dynamite, that kind of thing. So they make this casing, and then they detonate this stuff, okay? They detonate this explosive, and because of the shape, the pieces, the debris from that explosion, shoot in at the big chunk of fissionable material, and it blows up. Okay, because those atoms split, and when they split the atoms nearby, and those ones split atoms nearby. You get this chain reaction that results in the big mushroom cloud and the obliteration of anything nearby. Okay? There you go. That's how you build a nuclear bomb. Yeah, it's not that hard. Getting your hands on the material is hard. Actually, it's quite a bit more technical than that. That's just sort of the simple version of how you do that. Okay? Obviously, yes, it's way more technical than that. Even if you could get your hands on that stuff, you'd probably not be able to build one by yourself. Okay? Thankfully, because there's crazy people in the world who would want to if they could. All right? Okay. You know what? I think, guys, we'll leave it at that. We'll talk about Thomson and the other theories of the atom tomorrow. Okay? I don't normally end class early, but I've been talking at you all class, so I'm going to stop. Okay? If you have any questions you need to ask, just come on up and ask. Okay? And yeah, we'll move on tomorrow.